Lesson 818, No Bending, No Stretching, Rigid Transformations. In this lesson, we'll describe the effects of a rigid transformation on the lengths and angles of a polygon. Okay, let's get started. We're on page 32 in your workbook. This lesson is really a lot of information that we've talked about before. We're just adding on a tiny bit as we talk about something called rigid transformations here. So our learning goal right now is to describe the effects of rigid transformations. Describe the effects of rigid transformations on the lengths and angles of a polygon. On the lengths and angles of a polygon. Let's talk a little bit about what rigid transformations are. There are all kinds of transformations. We've really just talked about three kinds. And the three kinds of transformations we've talked about are the rigid ones. Those are the reflections, translations, and rotations. And again, there's other kinds of transformations like dilations that make figures larger and smaller. But we're interested in this unit on the rigid transformations, the three that we've been discussing. And to define a rigid transformation, it's a move that doesn't change any measurements in a figure. A move that doesn't change any measurements in a figure. No angle measures, no side lengths. A move that doesn't change any measurements in a figure. That's what a rigid transformation is. And I'm going to go ahead and draw some examples of rigid transformations and non-examples, but if you looked at my last set of notes, these are going to look real similar. Because rigid transformations just mean that I have congruent figures. I've translated like I have from the blue to the green. Let's just pretend those are the same size and shape. I can take that blue one and rotate it a little bit. And again, let's please just pretend that these are the same size and shape. So I could translate it, I could rotate it, I could reflect it. And those are examples of rigid transformations. And just like when we were talking about congruence, there's some non-examples as well. If I were to make a smaller figure that was the same shape but a different size, that's not a rigid transformation. And of course, if the shape were completely different, that's, clearly not a rigid transformation. Rigid transformations are the same size and shape from the pre-image to the image. I'm going to scooch up just a bit. And the measurements are really what we focused on today. That's what's new here. With a rigid transformation, corresponding parts, those are the parts that are matching in the two figures, in polygons, have the same measurements. So let's say we have triangle EFD, and that came from reflecting this triangle, flipping that over, and then translating it up and to the right. In fact, I'm going to use some patty paper and just kind of help us see what happened there. But these are rigid transformations that I'm performing on triangle ABC. Oops, that's P. So again, what they said was we reflected it over this horizontal line, and then we just translated it up and to the right. And we wound up with triangle EFD. And I can see which sides or which angles correspond with these 3 points. It's a little weird to see it, but my original point A landed on top of point E. So those are corresponding angles. And the same would be true of the other points that land on top of the new figures. Okay, so here's what I want to do. We're going to fill in all of the missing measurements in the diagram. And I want to start with the angles. Angle A is 64 degrees, angle C is 40 degrees, and angle B is 76 degrees. Now I should be able to use that to fill in these corresponding angles. So remember, we flipped this over and then slid it up. So when we flipped it over, I'm going to start with point B. When I flipped it over, it's now at the bottom. So angle F and angle B correspond to each other. So they're going to maintain the same measurement. That measurement doesn't change. This angle is going to be 76 degrees. Let's look at angle A. Remember, we reflected this over and then scooched it up. So angle A actually becomes angle E in the corresponding triangle. So they have the same measure. And that just leaves 40 degrees for this angle. Just like we did that with the angles, we can do it with the side lengths as well. And we're given the side lengths in this other triangle. This is 5, this is 3.32, this is 4.62. And if I can match these sides up with the corresponding sides in the pre-image, then I can know what these side lengths are. Let's fill those in now. Well, I think this side, when I flipped it over and slid it up, corresponded to this side. So AC and ED are corresponding sides, so they'll be the same length. Let's think about what AB corresponds to. When I flip it over and slide it up, it's going to correspond to side EF, 3.32. They have the same measure. And for that last segment, when I flip the triangle over and move it up, I wind up with segment FD. That corresponds to segment BC. So they're going to have the same measure. So how can you use measurements to decide if two figures will match up after a sequence of rigid transformations? Well, if the matching parts, the corresponding parts in the two figures have the same measures, then they're congruent. Oops. Your pen's running out. Hang on, let me get another pen. If I'm going to say corresponding parts, remember those are just the matching ones, in the two figures have the same measures, then they are congruent. And I'm going to use my symbol for congruent just to remind us that that's what the symbol is. So that's what we focused on today, more with the same kinds of transformations that you've seen. And the effect of rigid transformations on the lengths and angles of a polygon is just about nothing. There is no change in the lengths or angle measures of transformed congruent polygons.